This model shows how a refrigerant changes state, transferring heat in the form of latent heat as it does so. The refrigerant in this closed container has partially vaporized, and the vapor fills the tubing and the second container. The small amount of pressure in here acts on the refrigerant and prevents it boiling, even though the surrounding or ambient temperature would normally allow that to happen at atmospheric pressure. If we remove latent heat from the vapor with this iced water, the refrigerant condenses, and the pressure drops because the vapor in here takes up less space. The reduced pressure allows the refrigerant to boil at a lower temperature, and we can see bubbles as vapor is released. If we remove the ice water, condensing stops, the vapor pressure builds up, and then the boiling of the refrigerant stops. The fine point at which vaporization or condensing starts and stops, depending on which way the change of state is occurring, is called the saturation point. Because the liquid is saturated with heat just before the change to vapor. And when condensing, the vapor is saturated with heat just before it changes to a liquid. It only takes a slight change in either the pressure or heat content of the refrigerant to change the saturation temperature. If I heat the refrigerant with this hot water, the extra heat makes it boil, and the pressure in the tubing will rise. The increased pressure raises the boiling temperature, and when that's the same as the water, a new saturation point is reached. Changes in pressure or temperature directly affect the saturation point. If we were to imagine a situation where we wanted to transfer heat from a hot space to a cold space, then a simple closed system like this would do the trick. Refrigerant absorbs latent heat and boils in the heat exchange unit called an evaporator. The vapor travels to the other coil, the condenser, and gives up latent heat as it condenses. The liquid then returns to the first coil and the cycle continues.